Okay, so I'm going to talk about the detect backgrounds and for CPC and on behalf of the CPC study group. Actually, my colleagues already mentioned a lot about the interaction region design as well as a lot of background seen from the auxiliary point. And I'm going to tell you how those backgrounds would end up in the detector. Again, this Shah has already showed. I just changed the color scheme. And, okay. So I have to say this interaction region layout or design is quite preliminary. There are a lot of things we have to improve. We all understand the space is quite limited in this region, and that implies a lot of trade-offs between detector and the machine. And in particular, I would like to point out in the forward region, apparently those forward trackers are sort of placed down randomly. There requires a lot of work to optimize them. Definitely, we're going to come up with a better layout of the tracker and try to match it better between the vertex and the TPC or in the forward region. And definitely, we need 2 or 3 layers which are needed for the Lumical online monitoring or alignment. So in this talk, I'm going to discuss the the radiation background, which are always important inputs for detect design, and also sometimes this also concerns the machine design. For example, we have to think about the machine protection and some other measures we have to take. So this is also relevant for the machine design. And for the detector design, we are particularly interested in the detector occupancy, radiation tolerance, or radiation levels. Those things we do care a lot for the detector design. So far, we have investigated the most important sources, at least we believe at this very moment. For example, the pair production following the beam Strahlen effects, then beam loss, or sometimes it's also called off-energy particles, the backgrounds introduced by those particles. And synchrone radiation, this is always important at circular machines. And of course, we can easily extend this list to other sources. Okay, apparently even I cannot read this table. But there are quite important machine parameters we care a lot for the detector design. For example, the beam size, those kind of beam, the particles per bunch, those numbers, because they sort of are main inputs for the beam-induced backgrounds. And for the detector design, we are also concerned with the bunch spacing, which reads here. For example, for the Higgs operation, it says 680 and 80 nanoseconds. So when we design the detectors, we have to take those parameters into account. So actually the most important pair background for us is the so-called pair production. This is estimated as the most important background at linear colliders. Not an issue for previous detector, for example, LAP, or even for the super KKB, because the energy is so low. So it's not an issue for them, but definitely it's important for us. And the fact that, well, the phenomenon is the following. So the charged particles, we know they are attracted by the opposite beam, then they emit photons. This is called beam Strahlen. Then this process is followed by pair production. So basically gamma-gamma to electron-positron pairs. And what is the most important contribution comes from so-called incoherent pair production. And for actually, most of the electrons and positrons produced in this way are always with low energies and always in the very forward region. So we don't care because we know they will be confined within the beam pipe, and if we have a strong magnetic field. But still, there will be a non-negligible amount of particles that can hit our detector, so they become our radiation backgrounds. Sometimes we also talk about hadronic background. So gamma-gamma to hadrons, which is quite the important background for click. And at this low energy, this is not that critical for us. So how do we do the estimation? We have a quite nice program called GenPig. We use this GenPig to simulate this process, then with the output, we just simply feed them into the Geom 4 detector simulation. There's a caveat or feature that we saw recently, or we should have spotted this issue a long time ago. So because in our case, our beam size is much longer in the z direction, so that means a long time for colliding bunches to cross each other. For example, for the Higgs operation, the bunch length is about 3.6 millimeters. Now, because in guinea pig, there is no external field. That means our charged particles produced, they're going to travel over a long distance, a certain distance, without seeing the solenoid field. Yeah. So this is an issue. If you look at the position, so basically we take the output from the guinea pig and to see where those electrons, the charged particles, sit. And this is how we can sit. They're going to spread over the space in the RZ plane. Some of them can already reach the detector before even we run the detect simulation. And well, if you look at the situation for RC, those particles are produced quite localized. And be aware of the scale of the axis. Those are millimeter, 1, 2 millimeter, 5 millimeter. This is 35. So they are quite, for the RC, they are quite localized. So this becomes an issue because we cannot estimate precisely the background. So we send this request to the author of the guinea pig to try to convince them to implement the external field so that we can simulate better the background. Actually, this morning I had a quite good discussion with Daniel Schutter, so probably we should see this implementation pretty soon. So nevertheless, and I should also mention this issue becomes even more prominent at W and Z operations because the bunch lengths are even longer. So you're going to see even more particles spreading over the RZ plane. Anyway, we took what we were given by guinea pig and run the detect simulation and try to estimate of the background. We use the heat density, then total ionizing dose, and non-ionizing dose to quantify the radiation levels. Heat density because we are concerned with the detect occupancy together with the bunch spacing. And the total ionizing dose is an important parameter that we should take care for the electronics, radiation hardness of the electronics, and also surface damage to the silicon devices. And also the ionizing energy loss could introduce lattice displacements to the silicons. So those are important parameters that we would like to calculate. And in this case, we adopted the method used for the Atlas background estimation, and which is also the same method is also used for the upgrade. So and start to to run the simulation and get those numbers. And I have to remind you that a safety factor of 10 is applied everywhere for those calculations. Let's take a closer look at, because for example, we are most interested in those parameters at the first vertex detect layer, where the condition should be most crucial. So in the case of the Higgs operation, you can tell, okay, so the heat density per bunch crossing, I have to stress a bit, this is per bunch crossing for the heat density calculation. For the Higgs, it's slightly above 2 hits per square centimeters per bunch crossing, and the other numbers for the W and the Z. And similarly, we repeat the same calculation for NEO and TID, and the NEO for the Higgs is something about 1 to 2 times 10 to the 12th. 1 MeV equivalent, neutral equivalent per square centimeters, and those numbers are per year. And TID is about less than 600K per year. I'm going to continue a little bit and tell you the combined results a bit later. Because we have also other backgrounds. As I mentioned, there are also a contribution from the beam loss particles or off-energy particles, because particles losing a certain amount of energy, for example, due to radio bubble scattering, beam gas interaction, and yeah, I was repeating. And beam Strahlen, if those things, they can lose energy. And if the energy lost above the acceptance, then they can get lost. And some of them can get lost in the interaction region. If we are unlucky, they can hit the machine elements or detect elements and cause a particle shower. Then they're going to introduce a lot of backgrounds. So as already described in Sa's presentation, two sets of collimators are placed upstream, try to stop some of the alpha energy particles. And they have to be sufficiently away from the beam clearance area. That means the aperture size are subject to optimization. This is the effectiveness, the collimators. So we have two designs with larger and a smaller aperture radius. And if you can see, if we use an aperture radius of 1 millimeter times 1 millimeter, and we can suppress the background by an order of 2 order of magnitudes. So yeah, definitely we need those collimators. And even with the good thing is with those kind of collimator designs, we can get the remaining backgrounds even smaller than what we saw for the power production. So definitely we need them. And if we combine these two most important backgrounds together and we sort of come up with some numbers, and it says 2 hits per square centimeter per bunch crossing. This is the hit density for the Higgs operation. And 2 times 10 to the 12th, 1 MeV neutral equivalent per square centimeters per year. This is for the NEO, and the TID is about 1 megarad per year. Then you times number of operation years to get the total number. I should also mention the synchrotron radiation. So I already mentioned how we stop or sort of prevent some of the synchrotron radiation photons hitting directly our central beam pipe. So the most important SR photons are coming from the last dipole, bending dipole magnet, and also a small fraction coming from the Foxium quadrupoles. In this case, Sha showed some analytical results, and in this case, we actually we are using BDSIM to transport the beam, including both core and halo, from the last dipole all the way to the interaction region, and record the particles hitting the central beryllium beam pipe. As you can see, without anything in particular, we can see a lot of synchrotron photons hitting this surface and cause a lot of scattered synchrotron photons. This is quite dangerous for our detector. And so the idea is to come up with some collimators with high Z material and to stop those synchrotron photons. So this is this is done by our postdoc Curly, and he described how the collimator should look like. Roughly speaking, there are 2 important surfaces. This one needs to be parallel with the incoming photon or the beam, and the other, this extraction line, should not touch in our central detector. So these are so very basic principles that we need to follow. And by introducing 3 masks or collimators sitting at those places with respect to the IP along the Z pipe, and we can see quite good suppression of the synchrotron photons. And yeah, you actually can already see the positions, how they realize in this plot. You have to zoom in, and have to zoom in even further. So, but basically you can see, you can tell from those straight lines, upward lines, you can realize, well, those masks are at 4.2, so here. Am I right? No, sorry. Yeah. And so with those 3 masks or tips, we managed to reduce the number of photons per bunch hitting our central beam pipe from nearly 40,000 to only 80. So this becomes quite manageable. And a good thing for Franco mentioned the heating. So now we have much less power deposition in the central beam pipe, at least from the synchrotron photons. This becomes a lesser issue. And whether there are additional effects, home things that that's another story. We have to see how the calculation. Yeah, we have to see the calculation. Hopefully, we do not need any cooling in the central area. Then you have, keep them slightly away. Okay, this is already my summary. I have showed you the preliminary interaction region design. Of course, this requires further and a lot of optimization. And we have investigated the main radiation backgrounds that are important for detector design. And pair production is the most important, turns out to be the most important one, which is different from what we saw for the pre-CDR. In the pre-CDR, we saw radio bubble scattering was the dominant one, but in this case now, with the improved machine design, we saw pair production, because also with a higher luminosity, now pair production becomes the most important one, and this particular process needs to be revisited. Hopefully, after the fix or the feature implemented in GenPick, we can repeat some of the calculations. And those numbers that we have so far, so hit density, TID, NEO, that are needed for detector designs. Yeah, thanks.
Thank you very much. Do we have questions? Oh, we don't have a questions. It was that clear. I have maybe just a short one. If you have on the top of your mind some figures concerning the heat density of momentum electrons and converted pairs in the luminometer region. You gave us example for vertex. I'm just wondering about the luminometer.
Yes, we have some calculations. I can tell you a bit later.
Because of momentum electrons were the major source of background for lab measurements.
Yeah, I think with that the. Okay, now and I don't have the number on top of my head.
We can communicate
but
later.
definitely we can
okay,
provide the numbers.
Thank you so much. Let's thank Hongbo once again.
Thanks.
So.